So just so we know, I'm Sarah Wyatt. I am the Vice President of the OU chapter of Sigma Xi. And we have an announcement from Sigma Xi. Sigma Xi does grants and aid for research for students. So there's an application deadline is October 15th for the fall. These are for grad students or undergrads to do research in the sciences in particular. There's up to $1,000 for all fields. Plus, there's up to $2,500 for anything that's vision related, or $5,000 for astronomy. So whatever field you're in, these are great opportunities to write a small grant and to get that on your resume. It's also a great opportunity to get a little bit of money to do your own research. So think about that, and if you need help or whatever, you can contact me or you can contact Roxanne Malabruni in the research office, and one of us will point you in the right direction and get you started. Other things to note. Next week, we'll have a cafe conversation that will be Bill Condi from Interdisciplinary Arts, and his topic is fracking the Opera House, how they're using funds from fracking to renovate opera houses. So should be an interesting conversation, to say the least. And then in 2 weeks, we have the next Science Cafe, which will be David Tees from Physics and Astronomy, and he'll be talking about his work with laser tweezers. Definitely worth the time to come and check that one out. So with that, I will give you Savas, and I'm sure we're going to change this. Okay.
Good afternoon, everyone. Can everybody hear me well? Okay. So I teach engineering, electronics, electronic devices and materials, in particular at the School of Electrical Engineering and Computer Science. I'm very glad to see the crowd here, and I'm going to talk about a very broad subject matter today. Nanotechnology, whether it is hype or real, is it an opportunity, or are we getting getting a ride on a future technology that will never arrive? So this is a broad subject matter. I do not pretend to be an expert in every part of nanotechnology, which is, by the way, more or less everything we have known anything about materials since the dawn of time. If you think about it, nanotechnology is a culmination of all the knowledge that we can possibly gain and apply in dealing with materials and things that we can build using materials. I am an electrical engineer. I do have some interest in seeing things get small, better, and then serving the better good and improve human condition. However, there's a lot in it where I will talk about today. I will point you out what might be interesting, what might be perhaps good, but I'm not an expert in every one of these areas. That's a disclaimer. I should be honest and give it up front. So, if you look at the human history, particularly since Industrial Revolution, we had these waves of technology arriving and changing the world as we know it. Textiles at the early Industrial Revolution, then railroads, automobiles at the beginning of century, then computers, and we are possibly being washed away with another wave of technology called nanotechnology. That's what we have been hearing. I'm not going to talk about the nano car by Tato or iPod Nano. I'm sorry if you came to hear about the nano car. That's not the subject matter. Nano is a word that has been abused, let's face it, over the last 10 years. But indeed, these technologies, every one of these waves created big tectonic shifts in society, if you think about it. And indeed, nanotechnology is arriving at the initial ability to build microchips, small electronic and mechanical devices that has really made big changes in our lives. And hopefully I will like to get started with a short and fast video that summarizes that kind of time scale. Okay, so, but nanotechnology is about, just to summarize what nanotechnology is, it's about making novel materials and devices at the nanometer scale. We'll talk about it. Nanometer scale is really atomic scale times 10, maybe to 10 times 100. So we are really in the close proximity of the smallest dimensions that we can possibly deal with. And once you get those materials, next challenge in nanotechnology is to build structures and systems that will allow us basically do things using these novel materials. But nanotechnology doesn't end there. You need to now, NSF, National Science Foundation, explicitly states that nanotechnology is only nanotechnology if you are applying this to solve world problems. Not just exciting gimmickry or materials just to show up, but do solve problems. So why do we do that? Why is that intense drive to get small devices and nanosystems? Why NSF is so explicit about it? Because by the experience of the last 40 years of computer revolution, okay, we know that things that are built small, especially in technology, can be lighter, cheaper, faster, more efficient, and more accurate. And nothing is easier to understand, to explain this than the cell phones and smartphones of today. They have just got smaller. They are all the time more capable, but the prices are not going off the roof. I mean, more or less, the price range is the same, but we gain capabilities. Okay? If you compare the cell phones of 10 years ago with the ones today, you could absolutely see that there's a world of difference. Now, let's get to that particular video. I miscued, and we'll talk more.
In 1965, Intel co-founder Gordon Moore boldly predicted that the processing power for computers will double every 2 years. But Moore's law won't be true forever, and that collapse isn't going to happen in some distant future. It is going to happen within the next decade. First, we created the printing press, which was instrumental in bringing literacy to the populace. Steam powered the Industrial Revolution and quickly advanced across Europe and the United States. The first network started with dots and dashes and quickly became a worldwide net of telephone lines. The promise of safe, steady light laid the groundwork that resulted in electrified cities. The automobile accelerated the speed of economic growth. Intercontinental travel became possible with the airplane. The television brought the world into our living rooms, allowing us to witness man reach for the moon and leave his footprints on it. The birth of the microprocessor brought the dawn of venture capital and the titans of Silicon Valley. High-speed computers allowed us to map the human genome, share stories, and connect with old friends while seemingly holding the world in our hands. We looked past the clouds towards the heavens, and the discovery of Higgs boson was a new milestone in our understanding of the universe. However, computer power and its phenomenal importance in advancing technology cannot maintain its exponential rise with its ever more microscopic circuitry etched in silicon. It will soon reach a final barrier, a silicon wall. And by 2022, we may be left impatiently finger-tapping for an alternative. Enter graphene, a two-dimensional material made from a single layer of carbon atom, the most flexible and the most conductive material in the world, which makes it the leading alternative to the silicon chip. It's not just computer circuit boards that graphene promises to transform. Graphene is also the strongest material on Earth, 200 times stronger than steel.
So, very fast video. A lot of developments over the years. Now, obviously, like any of these publicity materials produced by the companies who have interest in the end product, in this case graphene here, which was the 2010 Nobel winning material, Nobel Prize winning material, meaning the subject of the Nobel was discovery of this material. We are facing, in a interesting way, some crisis and some opportunities. The crisis is we've been really working with these products and devices and computers and smartphones that always get better. And we have been used to it. And we expect more. We are not satisfied having what we have. We want more functionalities, more things. Now, I'd like to just make it a little more interactive. Go around the room a little bit. What would you like to see in 5 years' time in your cell phones? Can I just kind of, it could be wacky ideas, it's all welcome. Let's just kind of have a discussion. What would be a nice thing to have in a cell phone in 5 to 10 years' time?
Better battery life.
Good, batteries. So charging once a week will be nice, wouldn't it? Okay, what else? Anyone else? Audio? So, okay, so good audio, right? Speakers that really blast and satisfy our needs. What about a projector? Having a cell phone that has an internal projector and you set it up anywhere, you watch your HD movie. That would be nice, right? What else? Printer, nice. Having a cell phone that has maybe some small ability to print on a small piece of paper, at least. It may not be easy for a large, but we never know. What else? How about having a personal medical assistant that I carry in my cell phone that is monitoring all the time my health conditions? If I am a patient of, let's say, high blood pressure, wouldn't it be nice that I'm being monitored all the time? Right? For my own needs, of course, not for somebody to eavesdrop to that particular data. That will be frightening, we know that. What else? Is there any other ideas, kind of expectations from cell phones in 5 years' time? DNA sequencing. So kind of, that would be nice for the CSI guys, right? They do take a DNA and they investigate right on, on their cell phones. Incidentally, I read a paper only about 3 months ago. Okay, somebody putting a solution of DNA on this touch screen of a cell phone, right? And this touch screen was made so sensitive, it would literally separate between different DNA concentrations. Touch screen, just nominal touch screen that you would buy. It was, electronics was a little fine-tuned, and a drop of a solution that has longer segments of DNA versus shorter segments of DNA was being analyzed on the touchscreen surface, and it was able to differentiate between the two. You never know. We may be closer. Okay, so just as you can see that we all have expectation and there's room to grow. However, unfortunately, with the existing technology, we are burning way too much energy on these little chips. Things are getting way too hot in those little laptops and cell phones and smartphones. We just have to switch to another material if you want to carry on the same trajectory. And graphene is one of those materials. And we'll come back to that. So some of you might be skeptical, rightfully so. You might say, oh, nanotechnology isn't new. It's been around hundreds of years. Indeed, that is true. Okay? Much of chemistry before nanobus was around, they were doing molecules and proteins and atoms. They were always dealing with nanotechnology. So what is special about it? It's really the focus, new tools, materials that we have never discovered before, and a willingness openly to attack and or conquer problems that looked really hard or distant in the future. So really, what is setting nanotechnology different from other endeavors of science and engineering is integration coupled with good timing and willingness to really tackle on difficult questions. And at this point, we don't have to convince people because we know miniaturization is gainful. It has a lot of different benefits. Okay? So on the right-hand side, you are seeing the first atomic kind of lettering or writing using scanning tunneling microscope. This is the one that got Nobel Prize for Binning and colleague that in I believe 87 or 89. So this was one of the fastest Nobel Prizes. And as you could see that basically xenon atoms on actually silver substrate was being positioned to make IBM letters. They work at IBM Zurich. This is another quantum coral. That's basically iron atoms, I believe, in a circular pattern. And what you are seeing, the wave patterns of electrons in between. And this is locally produced by Dr. Hula, Professor Hula in the physics department right on our campus. Okay? We did this within 10 years of that other picture. So this technology is very pervasive now. That may be a little surprising to you. Scanning tunneling microscope is this one today for students to play with. This is not going to do the atomic resolution. I'm sorry. It's way too noisy. Here, way too little, perhaps hot as well. In order to get atomic resolution, one needs to go to vacuum and really low temperature. But in principle, I have a sample of graphite there. And I should be able to do in room temperature, in a quieter surroundings, atomic resolution of carbon pattern of graphite, okay? In this little guy. And this doesn't cost more than $10,000, okay? So we'll come back to that, what it means for education, what it means for the masses who may be interested in getting their the new generation educated in nanotechnology. Because you can literally play with atoms, okay? So we have better tools. We have tools which we brought, and these are parts of our Nano Studio equipment. We'll talk about it a little more. And the next one is atomic force microscope. And the following one is electron microscope. Okay? All in desktop sizes. All easy to use. You are welcome to come and play with after the session. Okay? So when I say about being enabled by tools, I mean literally tools that we can really have and afford, have it and afford it. Yes, there are historically people did lots of different nanotechnology products unknowingly. This is Damascus steel. Those little patterns you find buried in the steel is actually basically nanometer size. They were able to produce this basically steel with this specific kind of processing to have all these nano elements integrated to it, and it was a very successful product for the time, at least for the time being. This is way before that. This is the Lycurgus cup in British Museum. So this thing looks really greenish when you look from outside, but if you illuminate from inside, it looks red because there are iron nanoparticles in the actual glass material. They infused with dyes that had iron in it. It was so small, they didn't know at the time. When we investigate this, we find actually nanoparticles in it. Stained glass in old buildings is the same technology. Okay? So, but there is definitely something new about science in nanotechnology, in nanoscale. We need to understand that in nanoscale, things are sticky, meaning we are really sensitive to the intermolecular forces. We are playing with atoms, don't forget molecules. We need to have accurate ways to measure and interact with the atomic scale. This is blessing and curse at the same time. You could make really atomic sensitivity sensors, but by the same token, it becomes too noisy. Anything that breathes, anything that touches, creates noise for these devices. Okay? It is shaky. Thermal vibrations make atoms vibrate, and that's throwing in a lot of noise. And it's lumpy. Basically, that you have energy quantized in such small structures. We do actually have ability to measure in low temperatures, but even at room temperature, these quantum mechanical features are showing up. and it's crunchy. Crunchy means basically there's so much surface on these materials. We'll talk about this. The surface is so large, it is incredibly rich in phenomena. Okay, now what you're seeing is actually a piece of silicon film, okay, versus a 10 nanometer silicon cube. If I can cut silicon crystal, which is the microchip material, and then make tiny little 10 nanometer cubes of it, and count the number of atoms on the surface versus atoms buried deep in the structure. So basically, if I do that, I'm not going to go through the math here, but if you count the surface atoms versus those inside here versus this larger film, you find that there is orders of difference. So in silicon film, about only 3 in every 10,000 atoms are on the surface. In this little 10 nanometer cube, about 10% of atoms are on the surface. So I have a lot of surface. And that's the gain I'm getting, and that's the responsivity that I'm gaining out of this. Okay, I have unique materials now. And by the way, I'm showing all this to hopefully convince you this is not all hype. What are these materials? We'll see another short video maybe to show some realistic examples, but these are some pictures. You are seeing on the lower left a few nanometer wide quantum dot. That is a cadmium, I believe, sulfide quantum dot, perhaps a total of 100 atoms in that pack. Okay, 100 atoms. And in the middle, you are seeing silicon pillars, not more than 50 to 100 nanometer wide. They are as tall as about half a micron. On the other end, you see the carbon nanotube, a very popular material. It's a hollow tubular shape of carbon. Now, we'll see what applications they may bring us. But in addition to these tools that I have these materials. These are like my Lego pieces that I'm going to do a lot of interesting things, hopefully. But there is also a timing issue for nanotechnology not to become a hype, but a real sort of device and real, products that we can hold. We need to recognize also microelectronics have been around 40 years. Within these 40 years, we've been able to have cell phones, laptops, and everything, right? But this has come to a stage where by the year 2000, we were already getting 100 nanometer transistors built. So microelectronics have already got to the scale where molecules, chemistry, biology naturally finds it at home. So suddenly electronics have products and devices on the same scale of biology, okay? That is an enabling and an interesting medium. Why? Because I now, as a biologist or as chemist, I am on the same scale as the other man-made products, and I can take advantage of the confluence. And what are these? I can make molecular size memory cells, so that my USB flash memory, okay, these flash memories have gigabytes of capacity today. That's because every transistor on them is about 32 nanometers today. Okay? If it wasn't 32 nanometers, we would still be playing with 10 kilobyte memory sticks maybe. Okay? So there is this confluence. What I'm trying to get at here is the timing is right. Everything is kind of meeting at the right time with all these tools and with all this product, all these capabilities. And now the confluence is important because I'm going to tackle these big, bad problems that I have to deal with on Earth. Energy crisis, always a problem. Water, limits of water, fresh water that we can have access to. Climate change issues, poverty, that basically creates a host of problems. The medical and security issues, all these problems are waiting answers, just like our cell phones. You have some expectations these problems will be solved. Can nanotechnology help? And if so, how? Let's take a look.
This is a man-made motor, a motor so small that more than 6,000 of them would fit on the head of a pin. Welcome to the world of the nanometer, a unit of measure that is 1/billionth of a meter.
A nanometer is pretty small. One of the best analogies that I like to use is to compare it with a human hair. If you take a hair off of the top of your head, you can see that it's very thin. And now if you take something that's 100,000 times thinner than that, that's a nanometer.
The ability to observe and construct things this small is at the heart of nanotechnology. And what scientists have discovered is that at the nanometer scale, everyday materials start to act in unimaginable ways. For Jeffrey Grossman, a UC Berkeley nanoscientist working with the National Science Foundation, that's exactly the draw.
The behavior of nanomaterials changes, or can change, when the size becomes so small when compared with a larger amount of that same material. When you have things that sort of start changing the way they behave, and now you have the ability to control that, it sort of opens up an entirely new phase space of material.
Suddenly it's like the periodic table projects out into a new dimension. It's not just that we have the list of elements, it's where we can change their sizes, and each size is a little bit different than every other when it's very, very small.
The fact that you can customize nanomaterials' unique behaviors has already turned nano into the buzzword of the decade. Some researchers predict nanotechnology could lead to faster computer chips, tiny medical devices that repair clogged arteries, and new filters to clean water pollution. As novel as nanomaterials seem, humans have actually used them for hundreds of years. For centuries, the colors in stained glass windows, for example, have been the result of a controlled heating and cooling process that adjusts the size of tiny crystals in the glass.
That's medieval nanotechnology. What's different now is that we have the ability to look on the nanoscale and see what's happening. That gives us an ability to design materials rather than to just find them by a kind of accidental process.
But understanding and controlling how nanomaterials act can be tricky.
Every time you chop the material in two, say you go from a crystal that's 100 atoms across to 50 to 25, each time you do that, almost all the properties of the material really change.
So these changes are very radical and quite dramatic. If you take a piece of a material, say silicon, and you look at that material, it looks kind of dark charcoal, so it's not that interesting to look at. But now if you take out your little nano ice cream scooper and you scoop out a nano-sized chunk of that material, and you look at that, all of a sudden it glows blue. And if you take a slightly bigger ice cream scooper out, it glows red. And so now you have a material that completely changes the way it looks, the color that it is, just by changing its size.
So the question is, why do nanomaterials behave so strangely? In the case of the nano ice cream scoop, the behavioral change happens when you start to make a material so tiny that its electrons are squeezed into a space smaller than they prefer. It's called quantum confinement.
The smaller you make the crystal, the higher the energy of the electron will be. Its kinetic energy is increased, and that can be thought of as making its wavelength a bit shorter and forcing it into a box where it kind of zips around more quickly.
Another factor that shapes nanoscale behaviors is the relationship between volume and surface area. Things this small have much more outside than they have inside.
The surface area of the material starts to skyrocket compared to its volume. And in fact, when you get down this small, most of the material could be just surface, and very little of it is actually volume. And the reason why that's interesting is that the more surface you have, the more reactions you can carry out on that surface, so you can do things like filtering much more efficiently. So you could filter water more effectively with more surface area.
Our ability to observe and change things at the nanoscale has led to a host of new materials applications and has even made it possible for scientists to begin building working nanomechanical machines like this motor. But in the world of nanomachines, nature is still king.
Some of the most fascinating things that we see on the nanoscale are the machines that nature builds on the nanoscale. Nature makes rotors and motors and things that operate on this length scale of a few nanometers by making protein assemblies and that have these interesting nanomechanical properties. If you look at the flagellum of a bacterium, it's a little nanoscale motor, and it has bushings and all kinds of little pieces inside there that is built very differently than the way we make ours. And they have some other tricks they're trying to decipher.
Ali Visatos and his colleagues are eager to understand and apply some of these new ideas to the real world. Among their goals, finding new forms of clean energy. Every minute, enough of the sun's light reaches the Earth to meet the world's energy demand for an entire year. This seems like a good place to start.
Photosynthesis and photovoltaics is surely the one where we have the most interesting conversation that goes on between how nature achieves this and how might we do it in the future. If we're to get our energy from the sun, we need to copy some of the lessons of nature, but we also need to find some of our own little tricks that we could apply.
Coming up with some tricks of their own. That's exactly what researchers are doing at Lawrence Berkeley National Laboratory's Molecular Foundry, located in the Berkeley Hills.
So, this goes a little longer in the interest of time. These are very popular YouTube videos anyway. You should be able to easily get hold of it. The basic message is we are learning now from nature. Nature is guiding us what else can be explored at the nanometer scale. After all the cells, all the biological and chemical compounds and biological processes and tissues and so on are built bottom up from molecule by molecule, adding and making more complex structures. So this bottom-up approach is what is exactly we can learn from nature and apply to nanotechnology so that we can tackle these big problems that we named in a list a few slides back. Now, over here, another important message to take away is I am an electrical engineer. I need to work with the chemists. I need to work with the biologists and physicists and so on in order to do this particular tricks and able to develop these new tools. It is impossible to work alone. You could see that everybody is bringing something to the table here. Okay? And that's really detrimental. We should get rid of those barriers between our disciplines if you really want to take full advantage of nanotechnology. It's just impossible to think that we will make big changes in nanotechnology, in the world with nanotechnology, if we stick to our own definitions of what our basically understanding of science and engineering is. Here's the pictures of graphene that I promised to you. Graphene is single atomic layer of carbon. Okay, it's like a chicken wire. Okay, all hexagons are the corners of the hexagon is the locations of the carbon atoms. This is the material that is stronger than steel, more conductive than copper, and so on. And this is the one that we have an eye on to see if we can do faster electronics in the future. But there was before that the carbon nanotubes, which is the graphene rolled up as a tube about 1 nanometer in diameter. And this material proved to be very promising as well because the electrons can travel like on the carbon nanotube in a very fast manner, just like graphene. And I can do also fast electronics and other type of tricks with this. And you could see that just alone, graphene and carbon nanotube alone can actually go and work with variety of areas of human achievement and interest. All the way from materials to the energy applications. Remember the new batteries we wanted for our cell phones? We wanted a week-lasting batteries. Nothing that we know natural materials will give it. We are going to have to deal with composite materials that probably contain things like carbon nanotube and graphite, and able to store a lot of electrochemical energy to extract. Electronics with faster computers and products. We can actually use carbon nanotubes themselves and the graphene as new materials to enable other nanomaterials and biotechnology. Can we deliver drugs right where they are needed in exact amounts using carbon nanotube capsules, for instance, and not exposing our body to excessive doses of radiation or drugs? Here's an example of the battery. Okay, that may last perhaps, these are all exploratory devices. They are not really working yet, or they don't have the full capacity, but what you can see here is those little pointy or porous structure. This is actually alumina. Aluminum oxide, very simple to produce. I could produce in your kitchen. That's simple in principle if you get the right amount of acid concentration and the right amount of current passing from aluminum. And now imagine every one of those pores, which are about 100 to 10 nanometer range, filled with graphene inside. This is precisely the similar technology the old batteries, AA batteries used to be. But in nanometer density, every one of them is a battery now. Or I could use all those specific nanoparticles and quantum dots to use them as colorful tags to perhaps indicate which organ is cancerous, which organ has an issue in my medical studies. Or I could use those particles to create tiny little lasers that are lasers eyes cannot see and embed it onto silicon chips. Why would that be an issue? Because our cell phones and computers are warming up too much and getting too hot. We need to use light to communicate on chip, which is the fastest and appears to be a plausible solution to the heating problem and communication bottleneck on chips. This would be possible with light integrated onto silicon chips, and every one of the big elements, of course, for communication, for memory or image or data processing will communicate with each other using light pulses. And it will not take much energy, hopefully, but it will be really fast. Those quantum dots could be itself a very sophisticated man-made sort of crystal of polymers covering the core nanocrystals, so that you can actually use the polymers and ability to react with the polymer and other organic materials to get into the cells, get into the tissues as needed. And every one of these cores and the materials can be engineered as we want it, and we can be able to, we should be able to detect them using their precise knowledge of their size. This is exactly what happens in cancer research. Ability to basically use gold nanoparticles that is literally sugar-coated so the cancer cells will readily accept them. When the cancer cells selectively get the the gold nanocrystals, this is like Trojan horse trick, okay? You are inside the cell, that is the cancer cell, because you coat it with the type of proteins that the cancer cell is willing to take on. Now, you could blast the wavelength of light that is readily absorbed by these nanoparticles and heat the cells only absorbing this gold nanocrystals. And now the cancer cells are only heating up and getting destroyed, not the healthy cells. These are some of the possibilities. In the interest of time, I'm going to pass this video, which was supposed to explain this very concept. In the interest, because I like to talk about lab on a chip. Again, remember the cell phones we would like to have for monitoring our health? Imagine a patient that has to go to a hospital for dialysis twice a week. Wouldn't it be nice that a cell phone-sized device is filtering the blood all the time? They can go around happily and lead a life which is not restricted. That should be possible with this technology called lab on a chip. literally, the idea is to bring all the lab elements on a chip, if you can. What are things? Filtering, mixing, diverting solutions, separating them, reacting them, taking the byproducts out, analyzing them, looking at them with the microscopes, measuring their electrical properties, and so on. All can be done on a single chip. And if, I mean, obviously this is going to be a very sophisticated and wet chip, so it's going to be different from your cell phone chips, okay? And they will be using less waste. They will be cheaper to run. You know that drug development takes 10 to 20 years because it's so expensive and it's so slow. With these devices, you could test minute amount of drugs every minute and in parallel, and you could do hundreds of tests a day. And here are some examples. These are real products that are coming up. Some of them are still large, some of them are still slow, but with the electronics being on the same surface as the wet science is a revolutionary idea. Okay? And as you could see that these are real tests, you could see that different types of solutions are brought in. This is the size that you are looking at. These are not really much bigger than a stamp size. And then all sorts of reactions and mixing on going on there, and the products are separated out. Imagine taking a device like this with a cell phone to a place where the nearest medical station is 500 miles away. You could save lives. You could use the same technology to monitor your health if you are a high-risk patient. But what about the hype? I've been talking about all the promise. And we know that there's some hype about nanotechnology. What is it? Obviously, with every new technology, sometimes subscription happens and people promise things that cannot be delivered. How many of you know a latest cancer research that promised a drug but never made to the market? There will be some cases of that in nanotechnology as well. But it should not lead us to disbelieve it and throw the baby with the bathwater. Okay? So this is basically fiction. You're not going to have tiny little robots that will go around your bloodstream and capture alien cells, okay? However, if you think about those carbon nanotubes that carry the payloads of drug, they are kind of tiny little passive robot. If you think about quantum dots get into the cancer cells and brighten them up in the medical imaging, that's kind of some little robot you can imagine, but not the nanorobots you see in the Bond movies, okay? Those are fiction. Those are hypes. In fact, if you don't believe me, listen to Richard Smiley, who basically a Nobel laureate. I think that could be more convincing. These are not going to happen. And all the hype and scaremongering, some books or some publications sometimes pointed in the past are really long past. What about space elevator? Doing a carbon nanotube bundle so thick and so strong and hang a weight on it and slingshot it to the, to the orbit. So you have a rope that goes to space now. Since carbon nanotubes are super strong and super light, that sounds a reasonable idea. But the problem is, International Space Station took about 15 years to build. Okay? When you want things in the space, you need international community to come together. What counterweight are you willing to put in the space? Okay, who's going to put it? How heavy is this going to be? These are really probably little out of realism. However, it's going to also cost a whole lot to build something like this. Good idea. Nothing hideous about it. It's just a little too overstretched to me. But again, should we forget carbon nanotubes because we cannot build a space elevator? So these are my messages, folks. Okay? Basically, nanotechnology is real and here. Okay? Your cell phones, your USB memory sticks have it. Okay? Our touch screens have it in some cases. And it is really rich with solutions to all sort of human endeavor, okay, challenges. We have new materials, we have new tools, like some of these microscopes that we'll play around a little more later. And, but there's, of course, some hype in all this, among all the good messages that we can give. And basically, the biggest importance, in my opinion, surprise in all this is science education, as we know it, can be changed totally. Especially, imagine tools such as the Nano Studio equipment over here, okay, going into high schools, where seeing atom is not a dream. It's not a abstract phenomena. You could actually give tools to the students where they can interact with the nanoscale. Okay? And for the first time, bring the science and the atomic scale into real classrooms. Okay? That should happen in 5 to 10 years' time. Why? Because this equipment was costing 10 times more 10 years ago. I'm not sure they will come down to $50 range. Okay? Probably not, but they will be really affordable. Nano Studio has a room in ARC 116B in annex building to engineering complex, ARC, Academic and Research Center. I welcome you all. It will be open to public. We will announce this with a big opening ceremony and web presence. You should be able to bring those interested in high school, welcome. Elementary school, if they want to check out their bugs in the SEM, they are welcome. Okay, we have the SEM for that. You can bring your super shiny surfaces to see if they are atomically flat. We can check those with this scanning tunneling microscope. If you are interested in finding out how soft your material, how sticky it is, we could use the atomic force microscope, this guy. Okay, so it will be available to public, but also our undergraduates. Our undergraduates will run it, not myself. Okay, we have Greg here, one of the team members in the Nano Studio group. So hopefully, we have on campus a tool now where you could interact with the nanotechnology in real sense, in nanoscale, in reality. So I'm going to just let this slide go on. This is explaining the atomic force microscope principle. In the interest of time and maybe just be able to answer your questions, I'd like to thank you for your interest. So the floor is open for questions, folks. Yes.
So there's a real concern with technology that the acceleration in new technologies that we have seen over the last century is actually de-accelerating now. So based on nanotechnology, besides just making the technology like my smartphone that we have better, can you envision new technologies that we don't know about right now?
Tough one.
I was thinking like the flexible screen
Right,
TVs
right.
that they were talking about.
Absolutely. Graphene is the ideal material for making conductive sheets of plastic because it's so conductive and flexible. You could make literally any size plastic, hopefully with the development techniques. I'm talking about even meters wide or feet, several feet wide area covered with graphene on plastic sheets. Those will be, yes, flexible electronics is coming around. Wearable electronics is coming around. Okay? I will not be surprised if every jacket or every coat or every significant, okay, let's say clothing item will have an electronic interface in the future to store your data. You don't want to carry maybe wallet. That's one idea. Medical information. What about emergency folks finding all your important medical information saved on a piece of tiny little graphene chip maybe? So that in the case of emergency, they don't have to ask your next of kin or lose time getting information. And they will not lose time because you already tell them you are diabetes in that chip patient.
These materials be made into garments, put in garments so that they be easy and clean
Yes. So, yes, the question is, can we make these materials in the garments, actually in the textile itself, so we can maybe change the way we, in a hot environment, it will open up and I will be able to feel better, and in a cold environment, it will tighten up and I'm not going to get really cold. Yes, these responsive textiles are actually currently ongoing projects in the community. Absolutely. Especially for the military personnel or people in the, let's imagine, firefighters, okay? We already know the shirts that don't get dirty, right? Because they have nanoparticles on it that roll off the water. Any questions? Oh.
Can you make like invisible cloth? Because I watched a video on the Japanese people, they make it invisible like
Okay. Yes, invisible cloth or cloaking, right? Cloaking devices. Cloaking device is possible. And that cloaking device is actually, it works on a scale, not necessarily at the nanometer scale, but it's close enough, hundreds of nanometer scale. It is possible, but it's difficult to make something, a cloaking device that will work for all wavelengths and for all directions. That's a work to be done in progress. You can get certain materials, basically what it does, it bends the light around and merges it again so it looks like the light traveling in a straight path. But it only happens for that wavelength of light for that particular angle. It may not work in every angle in every wavelength. But it's a good idea. It could, of course, it can, some of these ideas can be also scary, right, in the wrong hands. The other way around, graphene and aluminum oxide, right.
I've seen graphene superconductors. Are those sort of types, or are they actually possibly late-stage batteries?
Right. So question, if just to everyone to hear, graphene is also known to be superconductor at very low temperatures. It's been measured. Can it also gain additional benefit for batteries because it's superconductor and the batteries actually don't heat up, because batteries are heating up because of their resistive losses, meaning they are actually using some of the energy to heat themselves up. If graphene or other materials are superconductor at room temperature, yes. But if I need to cool them down to liquid nitrogen or even maybe cooler, that will not be okay for daily applications necessarily, but it could be important for the hospitals. It could be for scientific instruments. We can have this type of cooling features in those equipment actually. Not probably day-to-day uses. For superconductivity to make a big impact, and nanomaterials are candidates to improve superconductivity temperatures, bring them to room temperature, but we are not there yet. Not in a dramatic jump, but what we learn is there's this two-dimensional material class now, graphene being the first of them, and there are different classes of two-dimensional crystals. Some of them have very interesting properties to be investigated. We may learn from them because high-temperature superconductors, the highest ones we know, are actually many layers, 2D crystals packed in a very, very close range. In other words, they are layered structures. That layering might be a key thing to learn about. Yes, there are other elements that are like graphene, like that two-dimensional. Okay, silicon has in silicene form. There are experimentally not observed, but some of the simulated and anticipated structures. There is molybdenum sulfide, which is kind of two-dimensional. It's 2 or 3 layers of atoms connected together, but they are by and large a 2D alloy, basically. There are other classes of materials like that, indeed. Which one is the most promising? Graphene, by and large, is the most heavily invested and investigated now, but depends if we can play with other materials like, as I mentioned, for instance, molybdenum disulfide, and there's niobium diselenide, I believe. These are very promising materials. We don't know too much about them, enough about them to rule out graphene they're going to be becoming better than graphene. Good thing about graphene is carbon. It's not environmentally toxic. Okay, it's cheap. You could make, people make graphene out of wood stock. Okay? Okay. The question is, you're talking about this slide, right? Running slide. This slide is showing the question is, why is the mechanical movements are the key to the monitoring of the surface properties? Yes, tip will worn out if you keep using it. However, the electrical measurements that you are mentioning as opposed to mechanical measurements are the scanning tunneling microscopy. That's the scanning tunneling microscopy. This little guy is using that to pick up the atomic height changes and make up a map of the surface. That doesn't change. In that case, the current flow might, in the long run, blunt out the tip, but not the mechanical actual contacts. I'm sorry?
I have two questions.
Yes.
The first question is, what's the magnification that your SEM will get to?
Our SEM is not the most capable one in SEM class. Being the tabletop, you compromise a little bit. But even now, even then, this is 45,000 magnification. Best optical microscope does is 1,000. Okay? So this is 45 times better than optical microscope. I can see 30 to 50 nanometer features on this SEM. The bigger, larger, and more expensive SEMs are known to resolve 2 to 3 nanometers. I have one bigger one at lab that can resolve about 5 to 10 nanometer. My own take on it, it's not going to happen the way we expected, or this sophisticated, multi-armed, intelligent, tiny robots are not going to happen. However, if you think about medical capsules or medical devices that already take films and investigate the digestive tract, for instance, they are not nanorobots, they are micro or milli robots, and those exist. But not the atomic scale robots that do all sort of tricks and beam up images and capture the bad cells and maybe sequence a new DNA while it's going around, roaming around in your body. Those are overstretched, in my opinion. Yes, that's a good question. Can we make a nanothermometer so I make a very local measurement of my body temperature or my cell? Yes, these are possibles. Yes. So the question is, those gold nanoparticles getting into cancer cells, how do I heat them, right? Oh, where I want to reach, I want to use the molecular biology information there. I want to coat them with the proteins, protein signaling basically. Certain proteins have chemical signals where the cell readily accepts them as a good payload, good nutrition, for instance. And they use the Trojan horse way to get into the cell. They are using purely biomolecular signal pathways into the cell. Nothing electrical about it, nothing optical about it.
Okay, so you showed cadmium selenide, showed it with organic compounds like drug delivery. Is there an alternate to cadmium selenide? Cadmium is incredibly
Of course.
poison.
Okay. So question is cadmium selenide. Cadmium is troublesome because it's one of the most poisonous to our health, toxic heavy metals. The cadmium selenide as an alloy is stable. Okay, we don't want to necessarily, ingest them and have excessively, but they are not just going to pop into cadmium and selenide just because they are in our body. However, all these layers that on top is one of the aspects of it that it really seals it, right? Another thing is we have the Other elements, yes, we have more capable or equally capable, less toxic elements that can be. I have seen things like, for instance, zinc oxide, okay, cadmium, gold is another one. Gold particle is inert. Right. Well, you can then consider maybe silver, slightly less expensive, and there are other alternatives. I'm not a material synthesis in the nanoparticle end, but I can literally claim that there's at least a dozen very easily accessible quantum dot families today. You can buy off the shelf. You can make them, absolutely. Yes?
The video talks a little bit about using nanotechnology for capturing solar energy.
Right.
Can you talk a little bit about where that technology is now?
So very good question. I wanted to devote more time on that video. It went on to explain some of that aspect, but in the interest of time, I cut short. Yes, solar technology, solar energy is big need for us. Everybody believes in it. The question is, how do you get the solar energy efficient enough so that it can compete with other forms of energy, coal, nuclear, hydro, and wind, and so on. What quantum dots and quantum wires or nano wires and nano crystals do is they actually do a number of tricks inside solar cells. Number one trick is they absorb more light. They have so much surface, if the light comes in, it's going to bounce around a lot of times and it has more chances of getting absorbed. Number two, I can actually get quantum dots, smaller ones and larger ones, even larger ones, and tap into the different part of the solar spectrum. Meaning, solar light has blue, green, red, and beyond, right? Either extremes. I can soak up energy from those by engineering different quantum dots. The third one is, by the very presence of the quantum dots, it does improve the actual rate by which electrons and holes are produced inside traditional solar cells. So yes, the effort is there, but the basic input from nanotechnology to solar engineering, solar power problem will be, you may get sheets of solar panels so light, so cheap, I may actually cover wall-to-wall solar cells for a fraction of money. They're not going to produce the high capacity energy that you wish from rooftop elements, but they are so pervasive, they are so cheap. Because of their area advantage, they will equally be significant in energy intake. Okay, yes, I did mention, right, poverty, nanotechnology should be a tool to get rid of, at least, let's not be unreasonable in here, maybe ease some of the poverty problems. For instance, the information products will be more affordable. Education will improve in countries where it used to be very expensive and difficult, and they could not compete with the developed world because they didn't have these means. Cell phone, a good small tablet could be a life gateway for science and engineering and learning for many, many around the world. That's one aspect, actual information tools and information technology. Number two, a lot of places where poverty issue, there's problems like water quality and infant death, okay? Early detection of simple diseases, right? These are problems. Because human population is suffering there because of premature deaths and short span of life, the productivity is never comparable to more successful countries. So by dealing with other issues, energy, water quality, cleaning water cleaning in a cheap way, you actually help the poverty problem indirectly in that case. And also, in some cases, literally, new products can be made cheaply in this less developed parts of the world where this is a new business in a way. Last one. Okay, go ahead, please. Okay. Just for everyone to hear, this lab-on-a-chip technology and carrying that kind of devices to field and then treat people as needed elsewhere, away from medical centers, that technology today exists. In some cases, they exist. They are not working with cell phones. They are working with specialized equipment. But right now, in the next 5 years, you will see a lot of medical uses of cell phones. It's already happening. What is lacking in there is disease or problem-specific chips, medical chips or biomedical or microfluidic chips that will be appropriate for your problem, okay? That part is needing little more work so that you can, number one, have the right product and right responsivity and right price. But within 5 years, they will be more accessible. Within 10 years, they will be really driving the medical business, in my opinion, in the field medical care.
Thank you very much.
Pleasure is mine.
A little bit of time for people to play if they want.
Absolutely. So our Nano Studio equipment will be here. And in fact, as you could see that my students will turn that on and you could actually play and get to see how atomic force microscope scans the surface and makes images, how atomic scanning tunneling microscope can pick up the conductive islands on another metal. And we have the electron microscope. If you want to bring a sample, we can even put it inside.